It's my pleasure to introduce Rob Lazarsfeld from University of Michigan. He will talk today about quadratic equations and algebraic embeddings.
Thank you, Rob. Thank you for inviting me to visit your outstanding group in algebraic geometry. So what I'm going to talk about today is kind of a circle of ideas that's in between geometry and algebra. So the question is, what are the defining equations and higher data that are associated to algebraic geometry? So this is a subject that started very classically, and then in the last number of years there's been a lot of interest, and more recently sort of some higher dimensional results. So that's what I'm going to talk about. Okay. So let me move on. This here. Is it all visible? Okay. So I think a good place to start is with Chow's theorem. So Chow's theorem says this: supposing you have a complex manifold and you embed it somehow in complex projective space. So you take a
compact complex manifold.
Yeah, it's a compact complex manifold, sorry, and you embed it holomorphically in complex projective space. Okay, so what the amazing theorem of Chow is that you start with this holomorphic object, and what Chow says is, in fact, it's an algebraic creature. So that you can find polynomial equations, some homogeneous polynomials f alpha. So that x is the algebraic geometry defined, the algebraic variety defined by the f alpha. So it's the common zeros of this collection of homogeneous polynomials. Okay, so if we start with a compact holomorphic submanifold of projective space, then we end up with some defining equations. And so what you might be interested in asking is, well, what can you say about the equations defining this variety? So today we're mainly going to focus on questions of degree. And the advantage of stating the problem that generally is that it's easy to answer. If you state it like that, there's nothing at all you can say, because, as you might expect, because after all, if you just take any random collection of polynomials, then with a little bit of luck, they'll cut out a smooth subvariety, and those are the defining equations. So if you state the question like that, of course, there's nothing you can say. But there is a question you can ask that's maybe more interesting, which is, instead of looking at a random subvariety of projective space, the idea is if you have a complex manifold that admits some embedding into projective space, then it will actually admit a lot. So what you might ask is take a fixed compact complex manifold and ask about the defining equations of nice embeddings of that given manifold into projective space. Now again, there are various things you could mean by nice. So for example, there's been a lot of interesting work on when X is a Riemann surface and you look at the canonical embedding. But today I'm going to want to look at fairly general manifolds. And then the most natural meaning of nice is to look at very positive embeddings. So the plan is to look at very positive embeddings of projective embeddings of complex manifolds into projective space. Now let's have to do a little careful kind of this is going to have to move throughout this. Okay, so let's see. So let me next remind you what data it takes to discuss a projective embedding of a manifold, so that we can say it's going to become sort of more precise as I go through the talk. But what do I mean by a very positive embedding? Okay, so the easiest way to think about holomorphic embeddings is you start by choosing a holomorphic line bundle, so that's L. And then we're going to choose, so the space of sections of L is a finite dimensional vector space. And then we'll choose a basis of sections of L. And then having chosen that basis of sections, we'll map X to projective space by evaluating the sections at a given point X. Now, of course, you can't actually evaluate sections, but as a homogeneous vector, that's well defined. And then, of course, there have to be some conditions on L in the sections if this makes sense. But in our situation, that will be automatic. And so we use the sections of L to embed the X in projective space.
So you're always using an entire basis?
An entire basis, yes, absolutely. And so the takeaway from this is that for our purposes, what's going to happen here is that a holomorphic embedding in projective space is basically determined by a line bundle. And there's some condition on the line bundle, but we're not going to worry about that. That's going to be automatic. Okay, so then what do we mean by very positive line bundles? Well, a line bundle has a first term class, this. And so we can ask that that be represented by a 1-1 form that's very positive. And as we go along, the actual positivity condition will become clearer. But so imagine, at the moment we're talking about line bundles with very positive first-string classes. So those will define projective embeddings. Those will have some equations, and we're trying to say something about the equations. Okay, so let's look at the first examples that come up. So let's see here. Okay, so let's take C to be the Riemann sphere. And we'll take a line bundle of degree 3. So in the case of Riemann surfaces or curves, then C1, you can integrate it to get a number, that's the degree. Okay, so we'll take the embedding defined by actually the line bundle of degree 3. So the sections, if you think of S and T as coordinates on P1, the sections of this thing are just cubic monomials. So we embed P1 and P3 by evaluating those cubic monomials. Okay, so what are the defining equations of this? So this is kind of very classical. So there's a fun way you can look at this thing. So what you do is, so the coordinates on P3 will be T0, T1, T2, T3. You write down this matrix, so T0, T1, T2, T1, T2, T3. And what I claim is that this curve in projective free space is the set of all coordinates defined by the condition that that matrix had rank 1 or less. So what I'm saying is that, first of all, I mean, this is all elementary. If you plug in these things for T0, T1, T2, T3, this matrix has rank 1. And conversely, if this matrix has rank 1, you can find S and T that give you that. Okay, so of course, the condition that this matrix have rank 1 is defined by the vanishing of the 3 2x2 minors. So this curve is cut out by these 3 quadratic polynomials. So I think I'm indexing by the top variable. So delta 0, 1 is T0, T2 minus T1 squared, and so on. Okay, so that's the first example. So here we get 3 defining polynomials of degree 2. Okay, let's go on and look at elliptic curves. So these are one-dimensional complex torides. So you take C mod a lattice. Whoops, let me straighten this out. Okay, so we take C mod a lattice. That's another Riemann surface of genus 1. And so let's start with the line bundle of degree 3. So if you take a line bundle of degree 3, then it turns out to embed this curve in P2. It has 3 sections, and it's defined by a single cubic polynomial. So this is the famous embedding of an elliptic curve as a plane cubic curve. On the other hand, if you take a line bundle of degree 4, then you end up in P3. And here it turns out that E is defined by 2 quadratic polynomials. So there are 2 polynomials of Q1 and Q2 of degree 2, and E is the common zeros of those. Okay, so this is actually a rather typical thing that happens. If you take you start with a line bundle of a certain degree, you get defining equations here of degree 3, and as the line bundle increases in positivity, the degrees of the defining equations go down. So you end up in quadrats. And of course, we're not going to ever have any linear defining equations, otherwise we would be in a linear subspace. So the lowest possible degree equations you could have is degree 2. And this is a general fact. So the general, I probably better to call this a principle than a theorem, but anyway, it's a proof statement. The general principle here, that sort of summarizes a lot of classical work, is that if you take any smooth variety, any smooth compact complex manifold, and you can embed it in projective space, if you do that with a sufficiently positive line bundle, then you always end up with defining equations of degree 2. So the defining equations begin, as the line bundle becomes very, very positive, the defining equations end up having minimal possible degree 2. Now, this is a kind of a silly way to state the theorem. I mean, it's a true fact. But the interesting work here is to take some interesting class of varieties, like Mumford and Kent, who are interested in a billion varieties, and to get a kind of an effective statement. What actual positivity conditions do you need to get the ideal generated by quadrats? But in any event, the principle, which is all I care about at the moment, is that if you take a sufficiently positive embedding, you end up with equations of degree 2. And so a typical actual statement here is this theorem for curves, which I guess is through the Casanova, or anyway, it's a classical statement, that as soon as you take a line bundle of degree 2g plus 2 or higher, you end up with something embedded by quadrats. So you see, if we go back to the genus 1 situation, 3 is not 2 times 1 plus 2, so it's not defined by quadrats. But when you go to 4, which is 2 times 1 plus 2, it is defined by quadrats. And this pattern continues. Okay, and then you can actually go a little bit farther. You can, for example, ask what form do these equations take? And again, the first example we saw turned out to be quite typical. So there's a line of work that's due, maybe it starts with Mumford and continues to various people, and maybe the sort of final statement was obtained by Jessica Sidman and Greg Smith. It says, if you're in this situation where you're embedding by a very, very positive line bundle, then in fact you can define the quadrics in the way we did originally. You can find some giant matrix of linear forms, and the variety will be cut out by the 2x2 minors. Okay. So, okay, we've actually answered our original question now. So what about the degrees of the defining equations? Well, once you have a sufficiently positive embedding, the defining equations have lowest possible degree. Now, I always think it's sort of not bad to end the colloquium a little bit early, but maybe this is too early, so maybe we shouldn't end quite yet. So there are a couple of issues here. So let me actually start with the second, and then we'll talk about it first. So, okay, so we've answered our question, why aren't we through? Well, first of all, it's kind of an algebra fact that one of the reasons, especially if you're an algebraist, that people might be interested in defining equations is that you'd like to use information about defining equations to read off invariants or other facts about your variety. And if you just know that something's cut out by quadrics, it doesn't tell you much. Because what's going to happen here is that the vector space of quadratic polynomials for your variety is going to be huge. And so just know, I mean, it takes some huge collection of quadrics knowing that the defining equations have degree 2 don't tell you much. To me, what's kind of a more interesting issue is this. So this is issue 1 here. So what we said is that when you start, if you sort of start imposing positivity conditions on your embedding line bundle, once you reach a certain threshold of positivity, then we've said that the defining equations all have minimal possible degree. But you might ask, then what happens if you have even more possibilities? So maybe something even better happens. So for example, if you go back to the situation of curves, what this Casanova theorem says is that if the line bundle has degree 2g plus 2, it's cut up by quadrics. So you might ask, what happens if you go up to 2g plus 3? And classically, people didn't really think about this. And I think the person who really sort of started this whole subject in this sort of modern development of this in the early 80s was Mark Green, who realized that you should see these classical theorems as the kind of the tip of an iceberg. It's the first case of a much more general picture involving higher syzygies. Okay, so now let me move on to syzygies here. Let's see, I think this is on. Yeah. Okay. So, syzygies. Okay, so let me just talk in an algebra setting for a second. So, okay, we start with this polynomial ring in R plus 1 variables. So those are going to be where that's the polynomial ring where all the defining equations live. And let's imagine an ideal. And just to fix ideas, let's say that this ideal is generated by a bunch of quadratic polynomials. So we have some ideal that's generated by quadratic polynomials. And we're thinking of these quadratic polynomials as the quadratic polynomials cutting up. Just imagine these are the ones that arise by cutting out our large degree variety. Now, the vector space of all quadratic polynomials is a finite dimensional vector space. And of course, these are going to mean we're going to choose, we're not going to repeat a generator. So these generators are going to be independent elements of this vector space. So we're not going to find any relations among these quadrics with constant coefficients, right? Because we'll take them to be linearly independent. On the other hand, it is very possible that there would be some relations among these quadrics, these quadratic polynomials, whose coefficients aren't constants but are other polynomials. So those are syzygies. So a syzygy among these quadrics is a relation of the form summation R alpha Q alpha equals 0. And now the R alphas are going to be themselves polynomials of some degree. And since all the Q's have the same degree, the R's will have the same degree, and we'll imagine that they're degree Q. And then we'll say that this is called a syzygy of weight Q. So I don't know if that's completely standard, but today we're going to make the weight the degree of the polynomial coefficients of the relation. And just the indexing here is nuts. Let's not go, if I try to change it, I'll not get anything right. So I want to count these as second syzygies. The Q's themselves are the first syzygies of the ideal, but what's important is the relations, and then even their syzygies, and the coefficients the degrees of the coefficients are the weight of the relation. Okay, so let's go back to our cubic, our degree 3 embedding in P1 and see what happens here. Now, this isn't the one I have to move, it's the other one. Okay, so let's go back to this degree 3 curve and see what happens. Okay, so so we take this P1. Remember, we were embedding it in P3. We're embedding it in P3 by these cubic polynomials, and our C was then the locus defined by the vanishing of the 2 by 2 minors of that determinant. Those determinants had a special name. I think they're called catalecticants or something. Okay, so how do we get syzygies among these? Okay, so here's what you do. It's a kind of a fun classical thing. So C is defined by these 3 2 by 2 minors. Okay, and now I want to claim that we can find degree 1, weight 1 syzygies among those minors. So we can find relations among these 3 polynomials with degree 1 coefficients. And here's what you do. It's kind of a classical thing. What you do is you take this matrix and you repeat a row. So let's repeat the top row. So now I have this matrix and it's got a repeated row. Okay, now you will agree that the determinant of that matrix is 0. Okay? But what I can do now is I can expand this determinant along the bottom row. And so I'm going to get 0. Now remember, my defining equations were the 2 by 2 minors at the top part of this matrix. So when I expand along the bottom row, I get a degree 1 relation, a weight 1 relation among those quadratic polynomials. And I mean, this is just a formal relation. You can plug it in, but this is where it comes from. And then there's a second one I can do, of course, which I can instead of repeating the top row, I can repeat the bottom row, and then I get another relation, another syzygy of the same sort. So this is the typical kind of thing that can happen. You get these defining equations, and if you're, usually you can't do examples by hand, but if you're clever, you can find polynomial relations. And so in this case, it turns out that this is it for the syzygies. There are no other syzygies. So here we have 2 syzygies of weight 1, and of course there's a minimal possible weight. Okay, let's look at our elliptic curve. So, So the interesting thing here was the degree 4. Okay, no, this is the easy one. The interesting thing here was the degree 4 embedding. So we take this degree 4 embedding of elliptic curve in P3, and if you recall, I think I should just leave it alone here. It was defined by the common vanishing of 2 quadratic polynomials. Okay. Well, here it turns out that there aren't any weight 1 syzygies. But there's one kind of tautologous weight 2 syzygies, right? So this is a commutative world we live in. So I can take the first polynomial multiplied by Q2, and that's equal to the second polynomial multiplied by Q1. So this is kind of what's called a causal relation. It's a kind of a tautologous relation. But it turns out that this is actually the only relation among these things. Any other relation is a consequence of this one. Okay, so here there are no syzygies of weight 1, but there's just one syzygy of weight 2. Okay. Good. So these are the second syzygies. Now, let's continue. So what you can do is each of these syzygies is going to be encoded by a vector. So here, this one would be encoded by T2, comma, minus T1, kind of T0. So you look at for each syzygy, you have a vector of coefficients. So here we would have 2 vectors giving us the coefficients of these syzygies. Now again, we're going to do things in kind of a sensible way, so these vectors are going to be linearly independent. They're not going to be any relations among these coefficient vectors with constant coefficients. But again, it's possible, and it's probable, not in these examples, that you're going to have relations among the coefficient vectors. So you repeat. So then the next step would be to form the third syzygies. So you take these coefficient vectors, and you look at the relations among them. And if the relations among the coefficient vectors the coefficients will be polynomials of a certain degree, and those would be the weight of the syzygy, and so on. So in this case, there are none, but in principle you do that, and you keep on going. And okay, so what we're really doing here is what in algebra is called, we're constructing the minimal free resolution of this ideal. So we're taking this ideal, and algebraically we're mapping a free module onto it by taking generators. Then we're looking at the kernel, we're mapping a free module onto the kernel by taking generators and so on. And so we keep in third syzygies, fourth syzygies, and so on. And what Hilbert's theorem on syzygies says is that if you keep going, eventually it stops. So if you're embedding into projective space of dimension r, the process stops after at most r steps. So you look at third syzygies, fourth syzygies, and so on. And it always takes so the number of steps is a little variable, but it's between r, the number of the dimension of the projective space, and r minus the dimension of the variety, the codimension. So here the codimension is 2, so we're only getting 2 syzygies. But so for all intents and purposes, you should think of the syzygies as going to step r. Okay, so that's some kind of general algebra. Okay, but now what's the idea? So let's go back. So this is what Mark Green thought to do. So remember, the way we sort of came to this is we were interested in saying that the theorem we discussed before said that if you take a sufficiently positive embedding, then you end up having the ideal, the defining equations have minimal possible degree, which is 2. So now you can look at these higher syzygies and you can ask, when do these higher syzygies have minimal possible weight? So that would be weight 1. So there's a definition here, is that what we're going to be interested in is when can we say that the first certain number of syzygies among the defining equations have minimal weight 1. So the definition people use here is we'll say that given this line bundle defining an embedding of our x, we'll say that x satisfies property n sub p is, first of all, p equals 1, which is a little bit exceptional. It should be the defining equation should have degree 2. And then p equals, we're asking that the first p modules of syzygy should all have weight 1. Okay, so the first p module of syzygy should all the relations that we get should have minimal possible weight. So if we go back to this rational curve here, because the numbering is confusing. So this is generated by quadrics, so that satisfies n1. But the syzygies have weight 1, so this satisfies n2. On the other hand, if we look at this elliptic curve, it's generated by quadrics, so that satisfies n1. But it doesn't satisfy n2 because the syzygies don't have minimal weight. The equations of the coefficients of the relation have degree 2. So this is not as kind of regular as the rational normal curve. Okay. So so we had this principle before that if you take a sufficiently positive, this is more than a principle, it's a theorem, that if you take a sufficiently positive embedding, then it's always generated by quadrics. And so what sort of Green's idea is that the same thing happens for these higher syzygies. So I'm going to state this as kind of a slogan, and then I'll state it a little bit more carefully. So the slogan version of this is that as we increase the positivity of this embedding line bundle, these higher syzygies, the first p higher syzygies have minimal possible weight, and the amount of syzygies that you control are linear in the positivity of the embedding. Okay, so now the time has come to state something a little bit more formally. Okay, so now I want to really have some way of making sense of this idea that you have linear in the positivity of the embedding. So what I'm going to do is I'm going to just look at a family of line bundles L sub d, and I'm going to fix some reference Taylor form omega naught. Maybe it should have integral or rational periods or something to avoid craziness. And so I'm going to look at a family of embedding line bundles L sub d, where the C1 is of the form d times this reference form plus any old thing, some fixed any old thing. It doesn't actually need to be d times something, but it should grow basically. So the positivity is basically growing like the dth multiple of the Taylor form. Okay, and so this is always going to be what L sub d is. And so again, this is a sort of not a real, this is a true fact, but it's really a summary rather than an interesting theorem. But so there was then a lot of work trying to understand, what happens with this property NP, and the summary is that you can find constants that depend on the x and the omega naught and the eta, so that the first p syzygies have minimal weight as long as this d, this L sub d, the sort of positivity of the line bundle is growing linearly in p. Okay, so that this property NP is holding linearly in the positivity. So again, let me state one real theorem here, which is the one that really got the whole subject started. So this is this theorem Green. So again, it's the case of curves. So again, we look at a curve of genus G, and again, the obvious thing to do here is just let the line bundle have degree D. And then this property NP holds when D is greater than 2G plus 1 plus P. Okay, so let's see what the numbers say. So if P is in 1, then of course the right-hand side is 2G plus 2. So this is this classical fact that a line bundle of degree 2G plus 2 gives you an embedding defined by quadrics. Then when you go to 2G plus 3, the relations among the quadrics become linear. So that was our rational curve, but not the elliptic curve. And when you go to 2G plus 4, the relations among the relations become linear and so on. Okay, and so as I say, what this theorem really is here is, and there was a lot of work by a lot of people in kind of extending that to other situations. I think I'll leave it. Yeah. Okay, so now we've answered. Okay, so again, we've come to a natural stopping point, right? We've understood the defining equations, and we've said that this picture about defining equations having low degree extends in a very pleasing way to higher syzygies. As you increase the positivity of the line bundle, the syzygies get kind of simpler and simpler. And this led to this philosophy, which I have to confess that I espouse, as well as others, that as the positivity of the embedding grows, the algebraic properties become simpler and simpler. You get this linear part of the resolution longer and longer. Now, had I been giving this talk, 4 or 5 years ago, I would have stopped now. And so maybe you wish that I might have fleshed out the beginning of it. But okay, but I came. So the nice thing about espousing this philosophy is that now I can give another talk espousing the opposite philosophy. So let's see if this is really the right philosophy. So let's see what's happening here. So, okay. So again, I'm going to assume that we're looking at this family of line bundles, L sub D, where the first trim class is basically D times the Taylor form. And X will have dimension n. Okay. Now, how many syzygies are there? So remember, I said that this number of syzygies is, for all intents and purposes, it's the dimension of the projective space in which you're embedding. Okay, what's the dimension of the projective space in which you're embedding? I should have sort of said something else there. Remember, how did we choose this embedding? We had to pick a basis for the space of sections of L sub D. So really what I'm asking here is how many sections does L sub D have? Well, that's governed by Riemann-Roch. And what is it? I mean, the dominant term is you take the C1 to the nth power, and then there's some factorial. But in any event, it basically looks like the integral of C1 to the nth power. Okay, what does that look like? Well, when we take the nth power, of course, what we get is a degree n polynomial in D. So in fact, the dimension of the projective space in which we're embedding is some constant times d to the n plus lower order terms. And it's a polynomial. Okay, but now, how many syzygies do we know about? Well, what we know about is we see the theorems I've been discussing are actually govern a certain number of syzygy modules, but the number of syzygy modules they govern is linear in D. So when n is equal to 1, which is the case that people, sort of the whole philosophy was sort of extrapolated from, for all intents and purposes, we understand the whole asymptotic picture, because there are a linear number of syzygies, and we know what happens linearly. But if you go to dimension 2 or higher, see what's happening is that this principle, where the number of possible syzygy modules there are, is growing like, let's say, on a surface d squared, but we only know that the first d of them are kind of well behaved. Okay, so the point is that this philosophy that people like me were espousing, if you think about it, it doesn't really give you the whole picture. It only sort of governs the linear part, whereas the behavior is potentially more interesting. And there was this kind of interesting result. To give you a hint that something is happening, there was this interesting result of Otavian and Pauletti. So they looked at this question. In some sense, the most natural higher dimensional variety to look at is projective space. And so you all come back to this example later. But you embed projective space by this line bundle d times a hyperplane line bundle. And so what this philosophy said, or actually in this case it was a theorem of Green, is that the first, actually in this case Green's theorem, is that the first d syzygies are linear. But they actually showed that once you get to 3d minus 2 or 3d minus 3, I think NP fails, it fails. So the first d syzygies are linear, but once you get to around 3d, they stop being linear. You stop getting weight 1 syzygies. So somehow what's happening in this case is that this nice behavior of syzygies is this sort of minimal complexity of syzygies are happening linearly indeed, but they're also failing linearly indeed. Okay, so the question this raises here is what can we say about, so let's fix an n-dimensional variety. We look at these embeddings into this projective space of roughly dimension d to the n, and we want to understand the asymptotic shape of the syzygies as d goes to infinity. So what can we say? And there are various questions you can ask. For the time being, I'm going to talk about just these degree questions. So just which weights appear. Okay. So this is, so now I'm talking about some work with long time, so some non-vanishing. Okay, so let's see what happens in n dimensions. So as before, just to sort of set notation, we'll look at x with dimension n, and we'll look at these line bundles where C1 is basically d times the Taylor class. Okay, and so it embeds in projective space of dimension r sub d, which is going like d to the n. And what are the possible syzygies? So again, the sort of which syzygies we're interested in, they're basically this many syzygies. So we have first syzygy, second, third, all the way up to r sub d. And we want to understand their weights. Okay, so there are two general facts. So the first, I mean, they're both quite elementary. So the first general fact is that for large degree, the only conceivable weights that could occur, the only conceivable degrees of coefficients of the syzygies that could occur are 1 through n plus 1. So you're never on a curve you could have syzygies of weight 1 or weight 2, but you can never have syzygies of weight 3. So that's an elementary fact. And what's a little less elementary, but still, is that if, well, this is due to Green and various people together, it turns out that you can completely control what happens to the highest weight syzygies. So for the maximal possible weight syzygies are completely under control. So let me just sort of state it a little bit vaguely, that you get, what happens is that these maximal weight syzygies only occur if the variety carries some holomorphic top-dimensional forms. And then there are only a finite number of these highest weight syzygies, and they occur for large values of p. So anyway, you can say exactly what happens. In fact, the number of them is the dimension of that vector space. But this is already interesting, and it kind of says what's happening for curves. Because so what's happening for curves is we could only get syzygies of weight 1 and 2, and basically these weight 2 syzygies kind of occur sporadic just at the very end of the resolution. So this actually already implies Green's theorem for curves. It says for most of the syzygies you only get stuff of weight 1. This is his theorem. Okay, but in higher dimensions, what's the sort of question that it leaves us with? So the question that we're left with is this. So let's fix a weight. So we only need to worry about syzygies of weight 1 through n, because n plus 1 is completely understood. And so the question is, when do we actually get a piece syzygy of weight q, where q is between 1 and n, when we take a very positive embedding? Okay, and the answer is that they occur for almost all values of p. So let's see. Okay, so here's the first non-vanishing theorem. So we'll fix a weight, and then the claim is that we can, if d is sufficiently large, we can find some constants c1 and c2 that depend on the geometry of the situation, with the property that if d is sufficiently large, then we get p syzygies of that weight for all p in a great big interval. And the interval starts at something times d to the q minus 1. And it goes all the way up to r sub d, except you have to end, potentially end a little bit earlier, minus something times d to the n minus 1. So there's this, when n is at least, well, this is for any n, but we get this huge range of p. For given q, we get this huge range of p for which we have syzygies of those weights. Now, this number is a little bit confusing, so let me try to explain what this says in the remark here. So again, let's fix a possible weight, and let's ask ourselves, so remember this NP situation was that all the syzygies had minimal weight 1, but now let's ask what happens with other weights. So the claim is let's fix now for an n-dimensional variety, let's fix any weight between 1 and n, and let's ask ourselves, for which p does it happen that we get a p, what's the proportion of those values of p for which we get a p syzygies of weight q? So for how many p's in this interval is there a syzygy weight Q, and what's the proportion of them? Okay, well I can compute the following. So this is R sub D. And how many of these things? Well, we don't know exactly which have syzygies of weight Q, but we do know that in this large range we have syzygies of weight Q. So when we divide by R sub D, which is like D to the n, then here the starting point, the sort of proportionally the starting point is like D to the Q minus 1 over D to the n. The ending point is like R sub D is like 1 minus D to the n minus 1 over D to the n. So what the theorem is saying is that this ratio approaches 1 as D goes to infinity. So what that means is that asymptotically in D, essentially all the situations, all the syzygy modules that could have generators in a given weight do have generators in that weight. So the kind of the sort of counter philosophy to what I said before is that somehow these syzygies are maximally complicated, but in the case of curves, there's only somehow one weight that they could appear in. And so there's a conjecture here. So this is a non-vanishing thing. We're just saying that in this large range of P, there must be syzygies. On the other hand, the thing that would be a nice picture that would kind of complete the asymptotic picture is that the conjecture is that this is really the sharp statement. So that conversely, if you're sort of asymptotically not in that range, you don't get syzygies. So this would give a complete kind of asymptotic picture of what's happening. Okay, now let's talk about the kind of the most natural example. So these are Veronese varieties. So what are Veronese varieties? So these are classical varieties. We'll take X in projective space, and we embed it in some giant, we take Pn and we embed it in some giant projective space by using all monomials of degree D. And the image is one of these classical varieties called the Veronese variety. And this is one of these classical things, and a lot of people have looked at syzygies of those. Whoops, no, I'm doing this. Wrong. Yeah, this is wrong. And so now the theorem we had before was just an existential, it was an ineffective theorem. But in this case, you can give a precise, you can make it effective. So this is the second theorem, which I think is found or also obtained in this case by Raymond. So, I mean, the specific numbers aren't that important. But the statement is, in this case, if you look at the syzygies of this very classical variety, then you get an effective statement. So it doesn't exactly matter what it is. You get the lower bound is some binomial coefficient, and the upper bound is some other expression of binomial coefficients. But let's just see how this works out. So if you take Q equals 2, and in two-dimensional things, so then if you work it out, you'll see that you get exactly this. So this is exactly this theorem of and Colloquium. So the conjecture is that for these classical Veronese varieties, this is actually should be the complete answer. That this is actually shown. But there's another, maybe in some way more interesting question you can ask, which is so projective space of course is a homogeneous space, and so these syzygy modules are functorial, and so they're representations of this special linear group. And so you can ask how complicated. Whoops, this is the wrong place. You can ask how complicated are they as representations of SLN, or SLN plus 1. So the philosophy here is that as the degree of embedding gets high, things become maximally complicated. So what you might expect then is that you could ask how many different representations appear in these syzygy vector spaces. And somehow the picture is that you should get a lot. And there's one result that's known. So this is by Mihai Folger and Jin Zhu. So again, you have to be a little bit careful what you do first. So here, what they're going to do is they're going to fix P, and they're going to let the degree go to infinity. And I should have said the dimension should be at least P plus 1, and I had a typo, so that should be D. So you fix P and you let D go to infinity. Now, if you let D go to infinity, fixing P by these Green's principle, the only weight syzygies you could have are Q equals 1. So the only question in this case you can ask is how many P syzygies do you have, how many irreducible representations are there in the P syzygy module? And they get the exact asymptotic, so it's D to the P. So they show that it's at most this many, and this is the actual order of growths. So it's somehow that you're getting a lot of different representations. And what would be interesting, but is not sort of beyond existing methods, is to sort of see what happens as you let P grow and D grow. I think you'd expect kind of exponentially many different irreducible representations. let me give a quick word about the method of proof for this non-vanishing theorem, and then I'll talk about the Benny numbers. So why would you expect this theorem to be true? Why do you expect as many non-vanishing syzygies? And there's kind of a very simple reason why it should be true, and we were unfortunately never quite able to make this a proof. But anyway, here's the intuition. So the idea is that what these very positive embeddings have is in common is this. You take a fixed hypersurface in your variety, and then you embed this variety by this very positive line bundle. And then this fixed hypersurface is going to be embedded by a very positive line bundle. It will lie in a very small projective space, because if this is n-1 dimensional, its projective space is dimension like d to the n is d to the n-1. So it has a much smaller. So you have these fixed hypersurfaces that lie in these vector spaces of huge codimension. Now, by induction on dimension, you can assume that you know what are the syzygies of x in its little projective space, and then you can see that this x bar in its little projective space. And then you can see that if you think of the syzygies of x bar in this big projective space, you would have exactly this picture where you get lots of different weights. And the expectation is that these many different weights of the syzygies of x bar in its projective space somehow translate into the syzygies of x in its projective space. And there's some exact sequence that relates these, and unfortunately, you're never able to show that the obvious map that was non-zero is non-zero. So the proof goes along these lines, but it's much more painful than this. Okay, so let me end with some more sort of fun, some Benny numbers. Okay, so what we've said is that if you take a very positive embedding of some variety, you get all these syzygies of very high weight. So now let's ask how many are there. So let's let kpq of L sub d, so the dimension of the vector space of p syzygies of weight q. And these syzygies are some cohomology groups, so these are called Benny numbers. Okay. So let's ask how many are there. So can we say anything about the asymptotics of these Benny numbers? So we fix q, and if we fix q, then we've got these various different p's, right? We've got different syzygies, and so we want to know how many syzygies are there in various spots of that given weight q. Okay, well, let's start at the first example. And again, it's strange that nobody really, I mean, in some sense there were formulas, but people haven't really looked at this, but it's a fun story. Okay, so let's start with curves, where, as you might expect, it can't, I mean, this kind of asymptotic thing can't be very mysterious. So, okay, we pick a curve of genus G, the degree of a line bundle is D, and then this R sub D is D minus G. And so the only interesting case here is syzygies of weight 1. So we want to know, as a function, what are the asymptotics of P of the number of syzygies, of the number of P syzygies of weight 1. Okay, so you ask Mathematica. I mean, there are formulas for this, so you ask Mathematica what they look like. Okay, so here are the syzygies of the genus 0 curve embedded by degree 0. And you see they're on the order of what, like 10 to the 18th. Anyway, so there are a lot of them, but you can see what's happening. We can do the same thing for genus 10. So there's the picture. Okay, so it's pretty obvious what must be happening here, right? Pictures don't lie, right? So clearly what's happening is that these things, in some sense, are becoming normally distributed. They're basically looking like binomial coefficients. Okay, so let me prove that for curves. So let me actually state the result here. Okay, so the statement is, so basically I want to say that they behave a little bit like binomial coefficients, but they're sort of become normally distributed in the sense of Mathematica, so that you're really approximated by a Gaussian is all I'm saying. So let me give it kind of a precise statement here. So, okay, we're interested in these line bundles of degree D, and what we want to do is, if the way you approximate binomial coefficients by a normal distribution is you have to go to the middle of the middle, r over 2, and then you have to go a fixed distance, a fixed multiple of square root of r over 2. So that's how you normalize these things. So we're going to look at the sequence of integers p sub d that's converging to r sub d over 2 plus a fixed multiple of square root of r over 2. So that means that this limit is what it is. And so a is some fixed number. And then the claim is that we can find some number with some expression. So there it is. It's basically 1 over 2 to the r. And we multiply, so this fraction times k p sub d1 converges to e to the minus a squared over 2. So this, and then, see, the point is that they're basically, I mean, not quite, but they're essentially formulas for these things, and they look like a polynomial times a binomial coefficient. The polynomial doesn't affect anything. Okay, so if you're an optimist, then what you would, or a fool, one or the other, or both, then what you would say, see, the whole picture here is that these, when you look at these asymptotic behavior of syzygies, you get uniform behavior. So if you're an optimist or a fool, and I think we try to be both, one we try, the other happens. The hope is that this is just the same thing happens on all varieties for every weight. So the conjecture is that exactly the same thing happens for syzygies of p-syzygies of any given weight on an n-dimensional variety. So for each weight, you can find some normalizing function so that when you take a piece of d approaching this thing here, you get this kind of Gaussian behavior. Okay. So there's not actually, well, okay, so let me tell you what the evidence is, and this is what you'll say, okay. So you could, of course, try to work out some examples on a computer. But the problem is that the numbers get big. So the biggest example we were able to do is the fourfold Veronese embedding of P2. So that already goes you into P14, and these are the Betty numbers. So they neither conclusively prove nor disprove the conjecture, I guess. Then you might ask, well, what examples did we work out? And it's, again, easy to answer. We don't know how to verify this in any actual example. So nobody knows how to actually understand the asymptotics. Even for the Veronese embedding of P2, one doesn't know how to compute these asymptotics. I mean, my dream is to get somebody on with a fancy computer person to do it like for D equal 20. People say I'm crazy because, you know, that's like, what, that's like 200 variables. And so that, but there's a kind of a funny line of thought that it's a little bit controversial, but there's a funny line of thought that may or may not strike you as providing evidence for the conjecture. And this is kind of a probabilistic picture. So this is what I want to handle. Okay. So let's say, so we don't know how to verify. So the conjecture is that these Betty numbers, as a universal phenomenon, become normally distributed, at least in this weak sense. And we don't know how to verify this in any example. Okay, so that's a pity. But we could ask, the next thing we could ask is, well, is this behavior the typical behavior, or would we have to be incredibly lucky for this to be true? And so we want to sort of argue that it's the typical behavior. So how do we do that? So let's think again what we've said about syzygies. So what we've said, if you have an n-dimensional variety and you take a very high degree embedding, basically the number of syzygies you get grows like d to the n, so it's r, it grows very fast. But the weights of the syzygies are fixed. So on an n-dimensional variety, for all intents and purposes, you just get weights 1 through n. You might have a few sporadic ones of weight n plus 1, will move those. So what you could do is you could look at kind of random resolutions having syzygies with fixed weights, and we could ask, what's the behavior of a random resolution with syzygies with fixed weights as the length of the resolution as the number of syzygies grows? So we fix the number of weights, which is like fixing the dimension of the variety, and we let the number of syzygies grow. Okay, and then, so this is somehow that's supposed to be what the typical behavior is. Now, what do we mean by random resolution? So there's a kind of a notion of, something like a notion of that in commutative algebra. So what would a commutative algebraist say is a random gadget? So, you know, typically resolutions or something might be described by some moduli space. There are some spaces of matrices satisfying some condition. You look at a general point of this variety and you see what happens. Now, there are two reasons why that's not going to be useful in our situation. First of all, you know, we're letting the number of variables grow. So for each, as the number of variables grow, we're looking at completely different varieties, moduli varieties. And the other problem is that we wouldn't expect. My feeling is that what happens is you get completely non-generic behavior. Okay. So there's another, what I want to argue is that we want to, so this is this work with I, maybe I didn't mention this with I and Erman. There's another way of looking at this, what you might mean by a random resolution. And not everybody in commutative, I mean, there's a theorem here, and not everybody in commutative algebra is convinced that it is evidence, but I think it is. So the idea is this. What we'll do is we'll look at modules over polynomial rings essentially with a fixed number of variables. And we're going to ask that the weights of the syzygies be, so in R variables, R is going to get R plus 1 variables, that's going to get very big. And we're going to ask that the number of variables goes up, but the weights of the syzygies that appear are fixed. Like think of n equal 2. So we have only syzygies of 2 weights, but the number of variables is getting very big. Now there's this very nice work. So I mean, traditionally nobody would have thought there's anything you could say about the resolutions of all of these things. But there was a few years ago, there was this very interesting conjecture of Boyne and Soderberg. And they had this kind of amazing idea that, well, you can take the numerical data of such a resolution and you can tabulate it somehow. And the table of any such resolution is a point in some big vector space. And they had this amazing idea that, of course, you can't expect to completely understand all the numerics of all resolutions. But they had this amazing idea that you could look at the cone in this vector space spanned by all tables describing resolutions. So they gave a very precise description of this cone, so that was a conjecture, and this was proven by Eisenfeld and Schreier. So I'm not going to say what it says in general, but in our situation, I'm cheating a little bit here, but basically, in our situation, the Betty tables that occur for these sort of models of these resolutions are parameterized by a certain number of numerical coefficients. Now, since we're only talking about the cone, since they're only describing the cone, we're really only describing the resolutions up to scaling. So we can only scale these things. And then after we scale, I'm cheating a little bit here, but basically, there's a certain number of like R choose n minus 1 numerical coefficients that are going to describe this, this resolution, the numerics of this resolution. And I mean, in actual algebra, the xi's are rational, but we could take them to be real because we're just going to be interested in numerics. Okay. So there's this space, which I'm going to call omega sub R. So it's this cube of dimension R choose n minus 1. And a point in this cube, a vector x equal x is parameterized by some n minus 1 element subsets of a set of R things. A point in this cube describes a formal numerical type of resolution. And what you should imagine, and so for each point in this, each formal numerical type of this resolution, we can describe the formal Betty numbers, the formal number of syzygies, repeat syzygies of A cubed. Now, what you should imagine is that when you have an actual real-life variety, like a variation embedding of P2 or something, you take the appropriate R, and you get some vector in here describing it. So a specific, I mean, I'm cheating a little bit, but basically, the first approximation, a specific vector, I mean, a specific variety is defined by one rational vector in this vector space, or maybe a line of them or something. And once we know that vector, then we can compute these KPQs. I mean, it's some formula. So once if we were to know what the vector describing an actual variety looks like, then we would know what these Betty numbers look like. But of course, we don't, since we don't know any syzygies of any variety, I mean, since we don't know what these look like for any x asymptotically. But okay, what you could do is you could say, okay, we don't know what are the specific vectors appearing for any variety, but we could ask, what happens if we just throw a dart at this thing and ask, pick a point. I mean, this is a cube, so just throw a dart at it and pick a point uniformly at random. Now, unless we were very unlucky, the varieties should behave like kind of reasonably random points. So the plan is to choose a point in this sort of this is the space parameterizing these coefficient vectors of resolutions. We pick a point at random, and then we also fix a weight, and then we can study the distribution of these Betty numbers for a random point. Okay, so let's look at some more pictures. The thing about this, all the pictures in the subject look the same. Okay, so here I did it for n equal, that's the point of my talk, right? So here I did it for n equal 2. And so I looked at a random resolution with R equal 14 and n equal 2. And you're working on Mathematica. You get this. Actually, I did many examples, and I tried to choose one that I liked particularly. So okay, so this is, and it's actually, so this is what you get. And then remember, what we want to do is this business of taking large degree embeddings is like letting the number of variables go up. So we get something that, but this actually looks surprisingly much like the one for P2, and I don't have an explanation for that. There's no reason it should. But even if you cherry pick less, they tend to look like that. But you go up to more variables, and then you see it really again begins looking normally distributed. And so let's see. I hope I haven't lost. No, here it is. And so the theorem is that that always happens. So I'm going to give a very informal statement here. But the theorem is that as you, so you fix a weight between 1 and n, and you let the number of variables go up. And then for most choices of x, these formal embedding numbers have this kind of become normally distributed in the sense of mathematical. I mean, they have this kind of, they're described by this kind of Gaussian band. So, okay, so this is, I mean, I'm not studying it. I mean, there's a real, actual, precise statement here, and then, you can decide whether or not this is any evidence for the conjecture that this, so there's no, I mean, these are all in vitro examples, whether or not you expect the in vivo examples to have the same behavior. And then I do, but then the interesting question is, like, why should they be points in the interior of this kind of voice over? Well, anyway, so now I will stop. So thank you very much.
Could you explain the relationship between these formal embedding numbers and the actual embedding numbers?
Well, okay, so it's a little bit, okay, let me try to, so I'm lying a little bit, okay? But this cube, these, what the Boy-Soderberg-Eisenberg-Schreier story says is that all kind of formal resolutions, all formal tables of embedding numbers are described by some numerical coefficients. So for all modules that could occur. And the numerical coefficients are after you scale in this cube. So if you have an actual variety, the way you should think about it is if you take like a Veronese embedding of P2, you get some R, well, n will be 2 in this case, you get some R, and this actual real-life example determines the point in this space. So every, I mean, there's some scaling involved, but every variety has its, up to scaling, has its own Boy-Soderberg point. So the actual, varieties that occur, you have this cube and you get some, a countable number of points in it. Okay, and so the point is I don't know, and then you let R go to infinity because you're letting the degree of the variety get very large. So each time you have an actual variety, it's determined by some specific vector. And we don't know any of the ones that actually occur. I mean, it's like, name a transcendental number. Right? I mean, so we don't know any of the ones that actually occur. But the claim is that if you can at least look at what the statistical properties are, and that's what we're saying. We're saying if you pick a point at random, then you get this normal distribution. There's certainly special points where it doesn't, I mean, there's special points where that doesn't happen. But, the point is, what I'm trying to argue is that the behavior where this kind of crazy conjecture for real-life varieties is at least predicting something that's kind of probabilistically likely rather than probabilistically unlikely. And the algebraists don't like this because this doesn't fit their notion of genericity. But I think, you can kind of really argue quite precisely that that doesn't really apply here. So somehow it's controversial whether or not this is really evidence for the conjecture, but I'm pretty convinced that A, the conjecture is true, and B, that it's evidence for the conjecture. But I admit that there's no real.
What would their notion of genericity be?
Well, look, so in a simple case, like you have some module, and it's described, let's say you have some module, and typically, so the simplest case is like when n equals 2, what you're really talking about is a module of the polynomial ring, and it really is described, it just has 2 interesting pieces. It has something in degree 1, well, you cut down by hyperplane sections. Then it has something in degree 1 and something in degree 2 or something. And so a module, so to give a module is you need to give 2 vector spaces and a matrix of polynomials between those vector spaces that describes the multiplication map. So in the simplest case, a module is described by some matrix of a certain size of linear polynomials. And now what you can ask is well, what's the behavior, algebraic behavior of the module you get if you choose these polynomials generally? And that would be, that's the kind of thing that would be the algebraics. But you see, I'm pretty sure that what happens is that the modules that arise for these high degree Veronese embeddings are completely non-generic. So for example, any variety is defined by quadrats. And it's dimensions of the quadratic forms for some variety are defined by some vector space of quadratic forms. But in the Grassmannian of all vector space subspaces of that dimension, it's completely non-generic. So I think there is some kind of notion of genericity algebraically, but I don't think you expect these high degree things to be generic in that sense. So I don't know if that, I mean, this is all expectation, but I'm pretty sure that that's.
Are you essentially conjecturing that all high-dimensional varieties look alike, but they're not strange?
In this very rough sense, that the Betty number is kind of, that somehow the picture is that I mean, maybe it's boring rather than interesting, but the picture is that once you go to this very high degree stuff, you lose all this kind of uniform behavior.
You're sure that it's not just you don't know the interesting examples?
Say it again?
Are you sure there aren't some interesting examples that don't behave like this?
Well, I think again, I mean, this is all conjectural, but the feeling is that once you go to high degree, you lose all the interesting, I mean, you know, any two things look alike. And my feeling is that somehow just there must be some simple explanation for this at the end. But, you know, it's all, you know, our non-vanishing theorem says that somehow once you go to high degree, you don't see any of this interesting, you know, like the most interesting work on syzygies probably is this stuff of clairvoyant canonical curves, where you can sort of, if you look at the syzygies of a canonically embedded Riemann surface, you can read off a lot of interesting and delicate information from which NP it satisfies. But but I think my feeling is that once you get to this large degree stuff, if you're looking at these kind of, you know, gross questions, it just becomes, the whole picture becomes uniform. But, you know, that might be wrong. Yeah.
So suppose that rather than considering the entire space of sections of these very positive line bundles, you instead were to project to a subspace.
Right.
Do you still get any kind of?
So that gets into these very different questions involving Casanova-Mumford regularity. Then you have to, because, you know, then you have to, there are interesting questions there, but it becomes very different. They're very different questions. You know, you're not going to get generation by quadratics. It's a completely different set of questions. And in some sense, it's maybe less natural geometrically. I mean, geometrically, you're going to, these are
linear subsystem would you naturally pick out?
Yeah, I mean, they're interesting questions. They're interesting questions, but the kind of questions that people have looked at are very different. And they just kind of, the kind of questions you look at is like, what's the possible weights of syzygies? What's the spread in weights of syzygies?
Could you say something about most on the left-hand side?
Okay.
Point at random, but is this a precise definition for it?
Yeah, so, well, let's see. There are different ways of saying this. One way of saying, one way of saying it is that you know, what the probabilists do is you let R go to infinity, and you put these, you know, there's some probability measure on this infinite cube, and then for almost all, I mean, that would be one way of saying it.
But so the set where it's somehow not, or where you expect it to fail, does that have any nice structure, or is it just
I mean, this is a completely element. I mean, this is unfortunately, this is an elementary. I mean, they're formulas for this thing. We're just saying that they expect, you know, you just take the coefficient. I mean, it's not very. What would be interesting, what would be very interesting, there's not a kind of a probabilistic reason for which this is true. I mean, we just look at the formulas and say, if you take the coefficients at random, what does it mean? The formulas involve binomial coefficients, and then you just muck around a little bit with the coefficients. So I don't have a good explanation for kind of why this is true. I mean, it's just that the formulas involve binomial coefficients, and, you know, aren't you lucky with that?
Aren't you saying that the conjecture is that the set where it fails is actually empty?
No, because I'm saying, because there's certainly, this is a numerical thing, so I can find numerical vectors where this fails, and I can certainly do that. But I'm just saying that for varieties, when you let R go to infinity, see, the reason the algebraists don't like this is that they claim that this statement is non-falsifiable. I mean, they say, how could you disprove it? You know, the people who have said that to me are also people that are not immune to that criticism themselves. So I got into trouble by talking about, isn't that the pot calling the kettle black?
Okay.